Where we're going next is we're going to talk about capacitors and how to determine how much potential difference they possess when they're connected in a circuit, how much energy they store. Because capacitors, when you have charged up a capacitor so that it has charges on both plates, one plate becomes positively charged, one plate becomes negatively charged, has an electric field between it. When a capacitor is charged, it is storing energy, and that capacitor can be used to deliver that energy later on. A good example of a capacitor would be in the flash of your camera. In your camera, in order to get a nice flash when you take the picture, you need quite a bit of current to run through it very quickly. Your battery isn't capable of pumping out the type of current that needs to run through it in order to give it just a quick flash. So what happens is when you turn your camera on, you remember you have to wait a second or two, depending upon how nice your camera is, before you can take the next picture. And that's because you have to wait for that capacitor to charge up. And what happens, the capacitor gets charged up, when you press the button to take the picture, it flips a little switch that connects the capacitor to the light bulb, and it quickly discharges through the light bulb. You get a nice little flash. So capacitors are quite handy in looking at energy and storing energy. So as a reminder, capacitor is two conductors. The example I told you before is two parallel plates. They don't have to be just parallel plates. There's a variety of ways to make capacitors, but two parallel plates is common. We call this a parallel plate capacitor. Very unique. We're going to look at capacitors first with just batteries, so a constant potential difference. When we have a capacitor and we connect it to some sort of battery, that battery forces charges to move throughout the circuit until the electric potential is the same on any one conducting surface. So for example, since the wire is a conductor, the plates of the capacitor are conductors, the charges are going to move until this end of the battery, the wire connected to it, and this end of the capacitor all have the same potential. So V on this left-hand side has to be a constant value once equilibrium has been reached. We're not going to worry yet about the time it takes for this to happen. It's not a completely instantaneous event. It does take time to charge a capacitor. It may not take very much time, but there is some sort of time frame involved. Likewise, the negative end of the battery, the wire connected to it, and the right-hand side of our capacitor all have to end up with the same potential. Now the potential on the left is whatever potential the high end of the battery has. The potential on the right is whatever the low end of the battery has.
The V's are right.
This V is not the same as this V. No. A battery is a constant potential difference. That means the positive end of the battery is always higher than the negative end of the battery. So for example, if this was a little AA, AA's are 1.5 volt batteries. That means if the lower end was 0, the upper end would be 1.5. Now, realistically, we don't really know what the potential is at either end, and it's not really that important. What's important to us is the potential difference. That's really all we care about, is the difference between the two. And our potential difference is the potential at the high end minus the potential at the low end. Notice, once it's in equilibrium, since the whole left side has to have the same potential and the whole right side has to have the same potential, delta V for our capacitor. I'm going to put a subscriptive C on it so we remember it's for the capacitor. Delta V for our capacitor, in this case, is equal to delta V for the battery. Does it make sense that that's the case? So equilibrium has been reached. Charges are no longer moving around in this circuit. When equilibrium has been reached, delta V for this capacitor has to be equal to the delta V for the battery. Now what happens in order to get that potential is charges had to accumulate on the plates. The only way you can have a delta V between the two plates of the capacitor is if there's an electric field in there. So realistically what happens is that the electrons get pushed out of the battery and they move around and they accumulate on the plate of that capacitor. But by induction, having a negatively charged plate, what is that going to do to this plate? It's going to become positive. It's going to push electrons away. So this plate becomes positively charged. So we get an electric field between the plates, and that electric field will relate to the potential difference on the capacitor. If you remember, delta V, I'm talking magnitude only. The electric field's constant, so it comes out of the integral sign. Integral of dr is whatever distance there is between the plates. Now, I know the equation has a negative sign in it, but we're just going to look at magnitude. Magnitude is really all that's important.